Okay, so I guess I'll get started. My name is Kevin McNamee, and today I'm going to talk a little bit about cracking command and control protocol of a peer-to-peer botnet. I work for a company called Kindsight, and I'll give you a very brief introduction to what Kindsight is, one slide, and then I'll go sort of straight into the rest of the presentation. The basic agenda for today is as follows. There's also, if you want, you can get a copy of the paper that this presentation is based on at the URL just over there. I believe it's up there at the moment. So a little bit about Kindsight. We're basically a company. We're owned by Alcatel-Lucent, founded in 2007. We have offices in Mountain View and Ottawa, Canada. I'm from Ottawa. What we basically got is a security analytics platform that service providers deploy in their networks. And the platform allows you to do security analytics. It allows them to run a malware detection service. And also we've got a new offering we're currently just announcing actually this week, which is a mobile security offering. The basic components of the system, which are sort of relevant to the talk, are we've got a snort-based malware detection sensor that the service providers deploy in their network. And that basically monitors traffic. It's a snort-based intrusion detection thing. It's got a customized signature set that allows it to look for malware infections in the residential network. There's residential subscribers, so that's the game plan. There's a security analytics engine they'll run in their data center. So the sensors feed information into the analytics engine, and that's that's how the service basically works. There's also a remediation aspect. They can bring their subscribers into a portal, and they'll take care of fixing the infections we find. So the basic gist of it was the impetus for doing this, finding this botnet, came from the fact that we're deployed in these carrier networks, and we have visibility into seeing what the network traffic is. And also part of that is we're very concerned about false positives. So as soon as we see anything strange in the network, our research team gets on it right away to sort of find out what's going on and make sure we're seeing valid infections. So that's how we came to sort of discover this botnet. Okay, so excuse me just a sec. The key to the malware detection service is basically the signature set that's deployed in the devices. And we update this signature set basically once a week in all the sensors we have in the network. And then we monitor it very closely to see if things are working properly. So as you can see in this here, we deployed a new signature set, and we see this sort of big spike in the infection rate. This sort of got our attention sort of right off the bat. We don't normally like to see stuff like that because it usually means something's wrong with the signatures rather than sort of a major event. As it turned out in this case, there was sort of an unusual, it was a new signature. The snort signature shown at the bottom of the screen here. And what it was telling us is that there was in the home net, which you see over here, let me see if I can, we had about 300 infected users in the home net, which is the network we were monitoring, communicating with about 60,000 peers on the internet. And that was sort of a fairly unusual pattern for us to see. But it was a pattern that did indicate that it was potentially a peer-to-peer type botnet. In a sort of a centrally controlled botnet, we typically see lots of users talking to a few servers instead of a few, relatively small number of users, 300, talking to 60,000 peers out there in the network. So that indicated it was a peer-to-peer net. So the first thing we do when we saw this, I'll give you some other things. We've been looking at this since basically December. We've seen connections to over 5 million computers out here on the internet from this particular little network here, just to give you an idea of the scale of this thing. Okay. Now the signature down here, this is actually a signature that comes from emerging threats, and we use those signatures are very good. It's actually quite a good signature, as you notice. It's sort of got, if you look closely at it, it's very specific in terms of the length of the data packet and the location of these hex strings that it's looking for. Okay, so it looks like a pretty good signature, but it's got these ports as any. So this is looking at any TCP traffic that's on there. So that is a bit suspicious. So we had to go on and make sure, check for false positives first of all. So we looked at that, and when we retrieved some data from the field, we found out it was only specific ports were being used, and the ports are sort of listed there. The initial packet was always 20 bytes long, and the areas you can see sort of in red in the packet there, they were always the same, always identical. And the peer on the internet responded with a packet that was always, again, the same size, and there was very common fields in it. So we looked at this, and we came to the conclusion that, well, first of all, it looks legit because of the limited number of ports that are being used. And second of all, it certainly looks encrypted because of the characteristics of the data. And it definitely looks like a peer-to-peer. So we asked the question, what is this malware, right? If you go back and you look at the signature, it wasn't very hard to figure out, because in there it says the signature comes, it's called the zero-access malware. So we knew right away what it was. So then we want to verify, like, our customers are going to come to us and ask us what we're seeing. So we did a little bit of research, went and Googled for zero access, and we found a really good report on the zero access malware itself from a number of sources, but one of the good ones we found was from Prevex. But when we looked at that analysis of what zero access did, zero access is a rootkit. It buries itself in a Windows system, conceals itself, and it's used to distribute malware. But there was no talk, and there was no discussion in the malware report there about a peer-to-peer protocol. So we figured we'd look a little bit deeper into it and see what was going on there. Okay. By the way, if anybody's got a question, ask as we're going along. Feel free to jump in. Just raise your hand, wave it around if I'm not looking at you, and we can answer any questions as we go. So basically, we saw this unusual traffic pattern. We realized it was probably related to this zero-access rootkit, and we wanted to sort of look into it a little bit deeper to find out what was this funny traffic it was generating. Well, where did that come from? So the first thing we had to do was find a sample to analyze. Now, at Kindsight Security Labs, we've got a collection of about 10 million malware samples. But more than just the malware samples, we've also currently got about 800,000 PCAP files that are associated with those samples. Now, that's less than 10%, but we're working to get a bigger library of PCAPs as we go along. We get the PCAPs basically by deploying the samples in a sandbox, watching the network traffic. Sometimes you have to tickle them a little bit to make them generate traffic, but that's the game plan. Anyway, so we run these, we took all of these 800,000 PCAP files, ran them against our signature set, this one signature, this the one that had triggered. And what we found is, we found 15,000 samples triggered this signature. I expected to find maybe a few hundred, but that was a very large number. And the interesting thing was that often everyone's familiar with the fact that all the antivirus companies call things by different names. You've got literally hundreds of thousands of different samples that are all really the same thing, just repackaged. But the interesting thing here was that the names and the sizes of the various malware samples were very, very different. So we sort of suspect that what this is, this malware that we're dealing with, this protocol we're dealing with, is actually being used and is bundled with a whole bunch of different malware. So it's like a common component. It's like a building block people are using to do this malware distribution, as you'll see in a few minutes. Okay. You can see over in the far side of the screen, that's just a sample of some of the names. These, by the way, are names that come from VirusTotal. Okay, so we take our samples, we run them through VirusTotal, they give us the list of names. So it's basically what the antivirus companies are calling it. Okay, so we just wanted to look at what the protocol was, so from that 15,000 samples, we picked one. Okay, because that's all we can sort of do an in-depth analysis of at any given time. And so what I'm going to talk about for the rest of the session is what happened when we did the analysis of that sample. Okay. There's some details on it. There's also, if you go to get the document off our blog, there'll be links to the VirusTotal and Threat Expert on this specific sample, and the MD5 is in there too if you want to, anybody's interested. So basically, we took that particular sample and we loaded it onto a Windows 7 virtual machine and we just executed it manually. just waited to see what would happen. Of course, we'd all sort of ready to capture traffic from it. Everyone's all sort of ready to go and observe what's going on. The first thing, there was 2 phases in the infection. The first phase, I don't think is really related to zero access at all. But the second phase seems to be, because this first phase doesn't involve any rootkit. The thing's right out in the open and it's just doing whatever it's going to do. So the very first thing it does is it creates this creates a directory on the C drive. And the guy's really sort of, who wrote this, he seems to be very into hexadecimal, because he's got this, you'll see these hexadecimal strings and various names and directory things all the way through it. So that's sort of a characteristic of it. Anyway, in there it created 2 files. One file, very creative file names. Okay. One file was called X, and the other was called @ or the @ sign. Okay. So the very first thing it did was it created these files, and then it created an entry in the basically making X the WinLogon shell. So now this X is going to be run every time you boot the system. Just did that right away. So when X is run, we took X and loaded it into a debugger to see what it would do. Okay, and it's really quite straightforward what it does. It basically injects a copy of the malware component. It injects it into the explorer.exe process. And I wasn't really that familiar with how this stuff was done, so I was sort of learning as I was going along here. But Microsoft provides a beautiful API for injecting code into various processes that you want. Okay, you start off, you do this open the process, so opens explorer.exe. It basically allocates some virtual memory. I mean, this is a process running over here. It opens a connection to explorer.exe. It allocates some memory over here using the virtual memory allocate. It takes a copy of its shell code and it writes it into the virtual memory. And then it says, go and execute that thread. It's really neat. I was quite surprised that it was so easy to do that. What the shell code then does is it unpacks this peer-to-peer module, which we then studied in a little bit more detail. Okay. Once it was running in explorer.exe, the next things that happened was it opened this file called the @ file. What the @ file contains was a list of IP addresses. Okay. And it was a list of 256 IP addresses. The malware running as a process within my Explorer process went through, it connected to all of those peers, or attempted to connect all of those peers. And as it turns out, once we decoded what it was doing, it actually, each of them returned a list of their 256 peers that were also, that they knew about. So this was its mechanism for basically figuring out who its peers were in the network. Okay? Once it did that using this getL command. Of course, it was encrypted, but we figured that out later. The next thing it did was it then went to the very first peer that responded, okay? And it downloaded a whole bunch of files, and it stored them in this directory, in this U directory over here. It created, in that subdirectory, it created a directory called U. Where is it? U. Okay? There's a little picture of it down here. And it dropped a whole bunch of malware files in there. And I know they're malware because we took them, we ran them against VirusTotal, and VirusTotal told us all about what they were, okay? And it then executed those. Some of those things did different things. I'll talk a little bit in the next slide about what those actually did. The malware then repeated this about every 20 minutes. So every 20 minutes it'd wait up, it'd go out and check who it was talking to in the network, all the various peers, update its list of who's currently active, and check to see if there's any additional malware to download. So that's basically what it was doing. The additional effects, this is the malware that it downloaded. There was nothing really that dangerous that came along with it. One of them, for example, this malware called, and the name, 8 hex decimal 80000 @sign. That's the file name that was used. And what it would do is it'd wake up about every 20 minutes, and it'd send a GET request to this website, to this web server. Okay? And actually, all that did was return a little GIF file, and actually copied the GIF out of the PCAP file that was returned, and that's actually all it was. So I think what this is doing is it's just trying to check in. It's being counted. It's saying, I'm here. This machine's infected. but I never actually traced it any further because it seemed I was more interested in what the protocol was doing. One of the things that was interesting about this particular thread when we traced it was in the debugger, there was debug code that was actually enabled in the malware. So if you looked at the log within the only debugger that we were using, the malware was actually logging stuff in there as it was going along, debug messages. And you could actually put breakpoints in there if you use the pause on debug string. So if you're ever doing any malware analysis, the guy that programmed it might have left the debugging code still in there, so you can take advantage of that and see what worth looking at. I didn't think it would be that simple. Anyway. The second thing it did was it was a click fraud scheme. And basically this was one of the other malware files that were downloaded. It's got that name up there. And every 15 minutes it would wake up, it'd issue a get to a specific URL. And that would download basically a configuration file, which was a bunch of other URLs, which were starting points for an Adclick fraud. This particular malware would then go through, and it would basically go to all of those websites, and it just basically, go through, through all the various links that it could find, clicking on stuff. So the assumption being is this is an Adclick fraud. It would wake up every 15 minutes, and it'd get another list of starting points, and then it would take those and go through and click on all those. So that was what it was doing. Again, not really that damaging to the system, but the idea for this is that it owns the system, and it just sits there, and it makes a little bit of money by clicking on things. In the background, doesn't really try and sort of disturb what the user's typical experience would be. Wakes up quietly every 15 minutes and does this thing. So while all that was taking place, there was the second phase of the infection. And this part, I think, is related to the zero-access rootkit, because this was a little bit more nefarious in terms of what it actually did to the system. Okay, I was quite surprised, actually. It was that I didn't realize that the exploit it was trying to use here. But what it did was it leveraged the fact that people are going to sort of give things like the Adobe Flash Player, they're willing to click on a button to say, yes, I want to install this software. And it used that to get itself enough permissions to actually build the rootkit environment that it wanted to do. So the first symptom you saw, this was probably come up a couple of minutes after you installed it. You get this little pop-up here, okay? And what it's saying is, do you want to allow the following program to install? To be completely honest, when I saw this the first time, I said, oh, shit. I shouldn't have left Adobe running, because now it wants to update itself. It's going to screw up my PCAP file. Okay? And I clicked OK. But it wasn't Adobe. It was the malware. What it had done is it actually went out and downloaded a legitimate copy of the Adobe installer, unpacked it, dumped it into a temporary directory. In the temporary directory, it dumps in a copy of this msimage32.dll, a corrupted copy of that. And then it launched the Adobe install program. Now, the way that DLLs get loaded is it typically loads DLLs from the working directory. So when I clicked OK for Adobe to install, it loaded the corrupted, infected DLL from that directory, and then I was gone. I was completely owned by the malware. Okay. When this malware now had the permissions that it needed to build the rootkit environment, it created a hidden partition in the hard disk. It installed a shadow copy of, remember that command and control protocol we're looking at? Another version of that. This version ran on port 22292. The other one that was in the open, that was installed in the other directory, it was running on 21810 or something like that. So it was just like the same command and control, but a separate instance of it on a separate port, but exactly the same protocol. Yeah.
So do you have any theories on why they bothered to download Adobe at all, and why not just make their own red box and have all the stuff to be much better?
Well, I saw this and I said, well, I'm going to check. So I clicked on the more information and verified the certificate. So I verified that certificate, and it came from Adobe. This is the Adobe Flash Player is being installed. So that's why they do it. It's social engineering honestly, the first time I did this, I honestly believed that that was Adobe. And it got me. But it was good that it got me, because then I got to find out what it was doing. Now, the thing is, this has been reported to Adobe, and they've fixed it up. I think there must be some way that you can say, don't load stuff from the current directory. And so it no longer, when I try and do this, run this piece of the malware back in the lab, this part doesn't work anymore. All it does now is installs Adobe, which is a drag. But anyway. So the difference is the first one, in phase one, it attached itself to Explorer EXE and ran on port 21810. In this case, it attached itself to the system process, which is PID4, and it listened on port 22292. So it's a completely separate instance. In this case, the file system where it put the malware files that it downloaded and where it keeps the AT file and all the rest of that, they're in a hidden file system on the C drive somewhere. Okay. There is, by the way, if you want a little bit more information on that way of leveraging an existing application installation process with a signed app to allow malware in, you can look down. McAfee's actually got a pretty good paper on it, and there's a link there at the bottom if you want some more information on that. Okay. What this also does is there's a watchdog. This particular piece, the phase 2, it creates a watchdog process that runs. And again, there's another interesting link here. You can look at AVG in their threat report for 2011. They looked at this in detail, and they came to the conclusion that this extra process that shows up is actually a watchdog process. When I tried to attach my debugger to it, it killed my debugger and deleted it. It pissed me off. Anyway, so it's kind of it was sort of interesting stepping through this. It was good. It was actually good fun. It was enjoyed it. Some of the files that were created, just briefly, it's all malware, right? There was files downloaded on the first day. These ones here. These were the ones that were responsible for that subsequent activity. These ones down at the bottom here, they were downloaded on about a couple of weeks later. So the malware was actually, you could see it refreshing the files and downloading new stuff. And the ones down here looked like they had, it was actually DLLs with embedded JavaScript. I think what they do is they attach themselves to their browser and do sort of redirection and stuff like that. So they were kind of interesting too. Over here in this column here, you can see what VirusTotal thinks of them. And it's all malware. This table, by the way, if you're interested, it's in that document I referred to on our website, on our blog. The other file that's downloaded is this AT file, which is the IP addresses. It's just encoded in, basically, it's this binary. So it's got an IP address, and then there's a time it was last active, IP address, time it was last active, and it just repeats. This file, by the way, is not encrypted. It's only encrypts it once it puts it on the wire. Okay? When someone asks for, send me your current list of IP addresses, it then encrypts this and shoots it over to the peer on the network. Okay? Okay, so, by the way, what time is it? Just to give me a check. 10:24? Cool. So I promised I would talk a little bit about how we cracked the basically encryption of this. And to do that, that was a little bit more tricky than just, what I've described so far was just stuff that was happening to us. It was, we installed it and all sorts of things went a bit haywire. So what we had I thought the best approach to cracking the encryption was to get something that was reproducible. I didn't just want the malware sitting there shooting stuff out randomly every 20 minutes and stuff. So within any peer-to-peer type of network, each entity has both a client piece and a server piece. So what I figured the best, let's try and exercise the server piece of this malware. So what I did is wrote a little C program, and what it did is it connected to port 21810, and it took that 20 bytes of data that was common in all our signatures, and it sent it to the port. Okay? And of course, our little malware responded with its list of IP addresses. That was kind of cool. And so notice that was pretty good. So the next thing to do is basically we used the OLE debugger and attached it to the Explorer process. We could tell it was the Explorer process because that was the process that was listening on the port, so that was fairly straightforward. Now, and then basically put some breakpoints in to try and figure out where the encryption routine was, and we're looking for basically its encryption keys and stuff like that. And I can tell you that this is not a trivial task if something attaches itself to the Explorer process, because that's basically the process that runs your desktop. And anytime you move your little mouse out into left field, it can do really weird things. There's all sorts of threads running in there, and they're jumping up and down all over the place. So it was a little bit tricky, but basically what we did is we isolated where the malware thread was in the process, and then went through that and looked for function calls to look for where was it calling. It was obviously calling a socket interface to do the network I/O. So we located the various socket functions within that and put the breakpoints there. So we have breakpoints at all the various socket calls. We throw in a packet and wait and see what happens. And then from that, if one of the breakpoints trips, we then go through and trace it as far as we could until we sort of lose, the thread terminates, things disappear. Anyway, it took a few days, but eventually we figured out that this particular little routine here was the one that was called to do the encryption and decryption. Okay. And we basically, if you go back, you can sort of see it. You can't see it clearly, but it's just basically a whole bunch of moves and stuff. The key thing is at the bottom, there's that XOR instruction down there. That's the thing that actually does the actual encryption operation itself. The rest of it's just basically getting a byte that it's going to XOR with it. So we reversed engineered the algorithm. I said this is just the part that does the actual physical, like doing the encryption. But before that, it did a number of things. The first thing it did was it first of all initialized the buffer, which basically meant that it moved in a header into the buffer, and it moved the data, and so it had basically the clear text stuff in memory. The next thing it did is it computed a CRC, so it did that. And then what it did is it called this other function that we didn't know what it did at first, but basically what this other function did was it built this array of 256 bytes. Okay? And as it turns out, this byte array was the initialization for the data it was going to use to do that XOR to accomplish the encryption or the decryption. Okay? And it turns out that array was created using an MD5 of this hex value here. Okay? For some reason, and so this actually turns out to be the key. This isn't any normal encryption algorithm, by the way. This is something, the guy that wrote this malware, I think he invented it himself. I mean, it's not a very good encryption algorithm, but it messes it. He could have probably used like base 64 or something that would have been just as effective. But anyway, so you take this value here. This is basically the key. You feed that into this function here, init byte array, and it goes out and creates this 256 byte array of sort of random bytes. Okay. And then it calls this crypt routine. What effectively it is, it's actually a very sort of a naive stream cipher. So every time, basically what it does is for every character in the clear text, it gets a random byte of data and XORs it within. It just keeps doing that. And as it turns out, the way this algorithm works out, the byte stream that is used to do the XORing turns out always to be the same. Regardless of what the input data is, it's all based on this one key. So, and you'll actually find out also this key is stored in the header of the packet, encrypted, of course. But so you can always verify that if you've got the right key, because since it's always the same byte stream, it's always the same bloody value, So I said it's not very smart, but it was fun to figure it out. I remember years ago when the first presentation I ever gave, a guy I knew fairly well and respected told me, never show code. I couldn't resist. This is the encryption decryption algorithm which we built based on that gobbledygook down there. We got it into sort of this thing here. So the red stuff there, that's the byte array that is always the same, and it's always generated. And it's generated from that key value. Okay? And it's just 256 relatively random bytes. The little blue section over here is the actual encryption routine itself. And what it basically is doing is it's going through, it'll take it'll take a value from here someplace, and it will use that value to pick up another value, and then it will switch them around. In other words, it keeps changing that table. This table here gets changed as the encryption process goes on. It keeps swapping values back and forth through it. And then it takes, eventually, after you can see down here, it does this XOR, and that's what does the encryption. So that's basically the whole encryption algorithm. Okay. Again, it's a pretty awful encryption algorithm for anyone. I'm not really a cryptographer per se. I don't know much about it. But I do know that since the byte stream is always the same, I mean, it's open to plain text, known text attacks. It's open to just everything. Figuring this one out is fairly simple and trivial. I mean, even if you change the key, it's a no-brainer to sort of decode it. Now, we didn't break the crypto algorithm by doing any cryptanalysis. We broke it by looking at the code. Which, I mean, I don't know. As I said, I don't know how to do cryptanalysis, but I do know how to look at code. Okay. So now we get to what does the command and control protocol actually allow us to do. And the command format is shown here. The first thing is we've got the first 4 bytes as our key, which will be encrypted, always to the same thing. The next 4 bytes is the CRC. And then we've got a 4-byte command, a 4-byte length, and then we've got a variable length data. Okay, so that's command. We then went through and figured out, well, what are these various commands? So we looked at the code that actually decoded the commands. And it's down here. It's a bit weird looking. As it turns out, these are the commands here. And the commands are coded in ASCII. Okay. And they're sort of reversed because it's a Windows machine, so it's an Intel machine, so it's little endian. So the numbers are all sort of in reverse. But basically, this is get F, get L, and SRV question mark. Those are the only 3 commands this botnet has. They're not really commands. They're more like, it's like the peer is asking for stuff. So you can say, get F is get me a file. Get L is get me a list of IP addresses that you know about. And SRV says, tell me all the files you've got. And it's that simple. It's very rudimentary. That's all this thing does. The actual decode routine when we looked at it, this is it here. What it's doing is it's actually subtracting off these values. A colleague of mine suggested it wasn't that the guy coded it up this way. This would just be a compiler optimization. It might be that, but I didn't think compilers were that smart, but they might be. But it's a bit weird. It just takes this byte value, it subtracts it off. If it's 0, that means it must be this command. It then subtracts 6 from it, and if it's that, it must be this command. And finally, it subtracts this funny value. If it's that, then it must be this command here. I just thought it was a bit strange. I don't know much about compiler optimizations, but maybe that's what it is. So that's the general format of the command. So here's the command specifically. When you do the get L, this is the key thing for finding out who's my peers in the network. Who else can I talk to? Okay? So when a peer responds, he'll respond with a list of IP addresses, and the format of those is down here and at the bottom. So the basic gist of it is that it issues this command, and when the peer responds, they will respond with a header that's exactly the same, except this will be, instead of a get L, it will be a set L, and then the length will be the length of the returned data, and then the actual data will be in this format here. So there's a number of IP addresses, which in this case was always 256, and then you have an IP address, 4 bytes, okay. 4 bytes actually in network order, and then at a time value. And the time value, I believe, when we sort of looked at it, looks like the time that peer last responded seemed to be based on a time starting in 1980 or something like that. I'm not sure why. I was expecting something like 1970 or whatever, but it's a sort of a strange time value. But it certainly is the time, because as they're updated, you can see this thing changing. So, and that information, when it retrieves all this, what the bot does is it goes out and gets all this information from the various peers it talks to, and it uses that in some way that I didn't figure out to update its at file, its at sign file, the one that's got the list of, so it kept that up to date. And then when some other peer contacted this one, it would then spew that back out. So that's the way they kept in sync as to who was out there. And the strange thing was, although there'd be one infected host might talk to hundreds and hundreds of other peers, they would only keep 256, the latest 256. So I'm not sure how it figured out how to do that, but it seemed to. The next thing was the getf command, which is the get the file. And it's basically the same thing. You had a getf command. The length was always 4. And then this piece here was actually a hexadecimal number. And that hexadecimal number was then translated into ASCII and used as the basis for the file name. Okay? All of these files were stored in the directory, this one under the subdirectory U. And you can see how the file name would be constructed. So it basically took the hexadecimal value and it added a .at on the end of it. You know, why it chose this format, I don't know, but it's obviously, that's just the way the guy decided. Okay. Any questions? Yeah.
So you were able to send,
I can't hear.
you were able to send commands to different peers?
The question is, were we able to send commands to different peers? And the answer is yes. We actually sent commands out to test how this was working to various peers out there. So that,
Did it have the self-destructs?
I can't hear.
Did it have self-destruct?
What?
Did it have self-destruct?
No, it didn't appear to. It seemed to be quite happy just to do its thing. No self-destruct. We did, not only did we see a little bit later on, I actually sent the get L command out to peers, collected the IP, harvested the IP addresses to map the botnet. Okay? So we did that too. And it seems pretty rudimentary, and there was no sort of other special things that it did. So this was how it downloaded files. When the file come back, when the peer responded with a file, this would be, instead of get F, it would be set F. The length would be the length of the file, and then the data would just be the binary, the encrypted file, right? What this indicates is that the way the malware works is the files have to all fit in memory. You couldn't download really, really large files because they have to fit inside the process memory. You know, so you can imagine if people were distributing very large malware, this mechanism probably would be problematic. The SRV command is basically a mechanism for the bot to ask its peers what files they have. Okay, and this was basically just the length is always 4, and what would happen is the peer would return. This is a sample of a buffer, and the first, basically have a header the same as this, and then the length would be the length of this buffer, and then the data would be what's shown in here. So here you've got basically, it's got the first number is an 800. That's an 8. So there's 8 files in the list. Okay. It's then got file. The format is basically file name, file creation type. File name, file creation type. The file names are coded in that hexadecimal. If each file name is an 8-digit hexadecimal number, which is encoded in binary here. And then the creation time is basically, again, from that strange time, 1980 being the base as far as I could tell. Okay. There was a couple of weird things that we did. We first of all used the SRV command on both. Remember, we had 2 versions of the malware running in the one machine. One's running on port 21810, the other one's running on 22292. One's using a file system we can see, the other one's using a file system we can't see. I had no way of figuring out where it was storing that. It was all encrypted on the disk someplace, didn't know where it was. But we could ask them different questions. So for example, we did know that the file names in both of them were the same, but the creation times were different, obviously, since the malware started and stopped at different times. When we deleted a file in the visible system we could see, it disappeared from the SRV list on port 21810, but not on the other port. So we could see it was definitely a different file system. We weren't sharing the same file system. And so that was interesting. So the next thing we did is we tried to drop additional files in there. Okay. Now, this is really weird. When we dropped a file in there, we could use the getf command to retrieve the file from the infected machine. But it never showed up in the SRV command. So we'd do an SRV command. Give me your list of files. Didn't see it. But we could retrieve the file. So we thought that was a bit weird, so figured maybe we'll trace that through. So we actually traced through the code. And we found in the actual code that there's a piece of code in there that when it was going through that directory, going through each file one at a time, it retrieves the creation time. And if the microseconds in the creation time is non-zero, it skips the file and goes to the next one. We wondered why. What we think is that this is a mechanism to prevent accidentally distributing files. So if you want to distribute a file, you have to put it into the directory, drop it in there, and set the microseconds in the creation time to be 0, and it's only then that that peer will tell all the other people about that file. I know it sounds weird, but that's what it did. I sort of could hardly believe that it was doing that, but that's what it did. Okay. So having played around with the various files, the next thing we decided to do was map the botnet. As I said at the beginning, on a live network, we saw there was about 300 computers. In the network we were monitoring, we're talking to a whole bunch out in the internet. But once we'd broken the crypto, we could then go out to all these hosts and we could ask them the question, what IP addresses do you know about? And they would respond. And we could decrypt it and get that list. So we wrote a little program that basically did that recursively. And I'm going to have to learn how to do multi-threading socket calls because most of the ones that it gives you don't actually respond. They're not quite active. They've been shut down or whatever. So, and when you're trying to make a connection to something that isn't there, you have to wait like at least 3 or 4 seconds to find out. So it took a long time. After about 24 hours, we'd found about 120,000 different infected machines out there. So I think I'm going to have to go back to the lab and learn how to do multi-threaded socket calls so I can speed up the process. Yep?
Have you guys ever looked into the root cause of this malware being distributed? How the machine got infected in the first place?
Oh. Yeah, how did the machine get infected in the first place? Typically, if you go right back to the sample we looked at, it turned out to be something about hot animal XXX, whatever. So I imagine people download it and to find out what that's all about. That's it. We just sort of installed it and ran it, but I'm sure you can probably get it in the standard ways that you could maybe. Another thing is, because this protocol is so common, we've seen it in a lot of different types of malware, it could be that you get infected with something else and it downloads this as part of its scheme. So I think there's a lot of ways to get infected with this. Okay. Yeah? Yeah, the comment there was if we're looking at hosts that don't respond, we should just sort of keep track of that and check them later on. That's a good point. The bottom line is, since we've been looking at this since December, and we've seen about, as I said at the beginning, about 500,000 connections to unique peers, 500,000 infected machines out there. Did we try to? No, we didn't do that with this many. They seem to be fairly spread out. They're all over the place. And by the way, this 5 mil. We were looking at this from the sensors we're using to get these stats from. We're looking at a network that's got about 150,000 users, and of those, about 300 or something were infected. So this is 300 computers talking to 500,000. So it's. So what's the purpose of the botnet? It's simply there to distribute new malware and update existing malware. That's the only purpose I can see to this. The botnet owner there's no command to tell it to do anything. The botnet owner simply drops files into these directories, sets the time properly, and then the distribution is automatic. Okay? So that's basically how it works. That's the purpose of it. There's a lot of different malware bundles seem to have this particular protocol being used, and I think it's a fairly common, fairly large problem. Yeah?
So you could use the same method to disable it.
Okay. Possible takedown? Good point. Okay. So one of the ways to sort of take this down is to basically create a poison pill. You find an infected host, drop it into the directory, and it's going to spread automatically throughout the botnet. That poison pill could kill the various processes, like shut down delete the X file, delete the address list, do all of that, take it down. You could also possibly attack it through the IP address distribution, but that might be, I think we'd have to do more research to find out how it selects which peers it's going to talk to. Remember, it gets a lot of information back. It only keeps 256. So if you can figure out how it does that, I'm sure that can be attacked too. And then you could, if you didn't want to sort of kill it entirely, you could always just replace the malware with files that are a little bit more benign. So that's basically it. Yeah?
You said that primarily they were doing click fraud. Do you do any analysis of the roles that they were connecting to see? Like, for example, a lot of advertising networks will have things like the ID of whoever it is that people should go to.
No, we didn't look at, other than the fact that we saw it visiting all these websites and basically crawling the sites and clicking on all the links. That's as far as we took it.
Or like the ownership of the sites, were they just all over the place? Or
Didn't really pay too much attention to it. If you want, I mean, someone else could do that. It's, I mean, it would be pretty interesting. We were more focused on just figuring out what did this particular bot do. Sort of like, was it, how did it work? Okay. That said, like the other malware, it could download. You can install. It'll install whatever its bot controllers give it. It will install and run. Yeah.
Did you figure out how long it kept a list of those 500K? How long did that 500K stay active? Or I guess each system only had 256, so the 500K was something.
Yeah. Each system only had 256. And it would check it would basically go through that list about every 15 or 20 minutes, refreshing the list. So it would wake up, it'd go out, talk to those 256, and then go back to sleep again. Okay. And the other side effects, like the click fraud and the other thing, those were happening in separate processes, and that was like a separate event, separate process taking place. Yeah.
So now that you've successfully decoded this particular botnet, what are your next steps as an organization? Are you doing any prevention, working with the ISPs that your clients are?
I could probably talk, if you want, we can talk about what Kindsight does after the talk. I think we've only got a couple of minutes left, so it'd take too long to explain that. That said, we've got, we offer a malware detection service for the service providers can offer to their customers. So that would be the approach they would take. The reason we did the detailed research in this is we have to know what we're detecting, and we have to be able to talk to our customers, which are the service providers, and explain to them, what we're seeing and why we're seeing it and stuff like that. So once we've done that, that's our job done. If they market that to their subscribers, then they can go to a portal and get it fixed and cleaned up. Yeah?
Sorry, what was the time frame for this research?
Time frame, we started looking at it at basically beginning of December, and put the paper together basically around about the end of January. Kept it under covers until today. This is the first time we've talked about it. Okay. Other than talking to Adobe about the fact that someone was,
For reference sake, the most common of these click fraud malwares
is which?
is TDSS.
TDSS. That's also one of the other names that's associated with this TDSS. We've got.
Particularly the one that would use rootkit. Obfuscation of that as well.
Yeah. Okay. I think TDSS is another. That's what I'm saying. There's a huge. We noticed, like literally, as I said, 15,000 different samples. Some of that was TDSS. Yeah. Can't hear. Okay, so Zeus is using similar types of techniques. That's good. Okay, so I guess I'm done. Thank you very much. It was,